You're listening to the Thesis Review podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to exploring the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since their PhD days. My guest today is John Schulman, who is a research scientist and co-founder of OpenAI. John co-leads the reinforcement learning team, researching algorithms that safely and efficiently learn by trial and error and by imitating humans. His PhD thesis is titled Optimizing Expectations, from Deep Reinforcement Learning to Stochastic Computation Graphs, which he completed in 2016 at UC Berkeley. We talk about his work on stochastic computation graphs and TRPO, how it evolved to PPO, and how it's now used in large-scale applications like OpenAI 5. Then we discuss his recent work on generalization in RL, and discuss the limits of scale, model-free versus model-based algorithms, GPT-3, and more. The Thesis Review is available on SoundCloud, Apple Podcasts, Google Podcasts, and Spotify. And be sure to follow on Twitter @Thesis Review. If you would like to support the show, you can contribute $1 at buymeacoffee.com/Thesis Review. There are links to his thesis and papers that we mentioned in the show notes. Here's John Schulman with Optimizing Expectations, from Deep Reinforcement Learning to Stochastic Computation Graphs, on the Thesis Review. If you could think about framing doing a PhD as a reinforcement learning problem, where do you see the current methods failing on this problem, or would they succeed?
That's an interesting question. So one interpretation of the question is if we design a task where in each episode you have a 5-year process of doing a PhD and you get a reward based on how good the PhD is. That would certainly be a hard RL task. I mean, you have a very sparse reward signal, not a very informative reward. You only get like one bit of information each 5-year episode. So I think if somehow you had a way to do like millions of episodes of this, you might be able to at least see some improvement. But I don't think that's a very realistic way to set it up. So I don't think you would have an easy time like optimizing a scientific researcher that way, or let's say a researcher AI.
So you just need a completely different approach.
Yeah, I think you would probably want a different approach. So I don't think we certainly don't learn this way. We don't learn to optimize for long-term goals by through anything that looks like discounted reward maximization. So I think
Right.
probably the key thing is to be able to work with shorter-term rewards and to get a dense reward signal that measures progress towards long-term goals. So you need to somehow have agents that form long-term goals, and you get a dense reward function that measures progress towards these goals, but you're not necessarily optimizing. Like you're not setting up the problem the way I described initially.
Unless you could somehow use everyone in parallel. But
Oh yeah, I guess if there are a lot of PhD students, you can get a lot of data.
let's talk about the long-term planning that you did. So before the PhD, what was your sort of background, and like when did you pick up an interest in machine learning and decide to take on a PhD?
I was interested in AI and machine learning since at least I was in high school to some extent, though the field was a bit less exciting back then. So I remember reading this book by Nils Nilsson, who is one of the pioneers, and he wrote a nice textbook that had everything from A star search to like some basic ideas of MLPs.
Hmm.
But the things you could do were pretty limited. So while I thought it was a very cool topic, I didn't really see what I should do there. And
Hmm.
yeah, then in college I got more interested in machine learning and also neuroscience.
Hmm.
And I ended up deciding to go to grad school in neuroscience, not in machine learning. And I figured I'd learn about how intelligence works by studying brains, maybe using some machine learning tools. But then once I got to Berkeley and started my PhD, I was looking around at different labs and so forth. I realized, well, I was around a lot of machine learning people, like uh, the office where I spent most of my time. I was surrounded by people in the computer science department working on machine learning. So I started to get more interested in that area, and then I eventually I was able to switch fields.
What was it about machine learning that drew you away from neuroscience?
The progress was much more tangible, and I found that I was more interested in the work that was coming out in machine learning, and I was finding it more insightful about how you might build an intelligence. So we might hope that by studying brains, we would learn a lot about how a mind works, but actually, it's obviously very hard. And I felt like I was getting more insight from thinking about machine learning.
Do you ever go back and try to think from a neuroscience perspective for machine learning problems, or?
I don't think about it at the level of computation, or at. I don't try to. Uh, I don't think of it by by trying to use some understanding of how the brain works. If anything, I
Mhm.
just think about what humans do and or what animals are able to do, and appeal to introspection a bit. But I don't
Mhm.
really use much of the knowledge I got from studying neuroscience.
I see. And then, so reinforcement learning specifically, um, how did you decide to kind of narrow in to focus on that?
I spent the first half of my PhD working on robotics and well, with some machine learning mixed in. So I was looking at things like I was looking at trajectory optimization and how to learn from demonstrations. And there was a little bit of machine learning, but not too much. At least it wasn't clear exactly how you would apply. It wasn't clear to me how you would apply powerful machine learning techniques to make the stuff we were doing better. It didn't seem like the bottleneck was learning some uh, learning some function from data. We just didn't have the data we needed to do anything. And also at that time, there's a lot of exciting progress in robotics. Like the Kinect came out, and there were some new better robots that were available, so people were making a lot of progress there, and I got interested. Like I thought that was a pretty exciting time in robotics. But then after a couple years, 2 or 3 years doing it, I started to feel like a lot of the progress was kind of illusory, or like you would you would go try to create a great demo for your project. You would show a robot doing something cool and impressive, and and then you would show how your new ideas were responsible for that. But in reality, it was um, these systems were very brittle, and most of the work came in just getting the whole system set up properly, so that you could
I
apply your
see.
small idea. Um, like that was only your idea was only like 5% of what made your demo possible. Yeah, everything seemed kind of it seemed like everything we were doing was kind of hacky, and um, at that time the ImageNet results came out from Krzyzewski, Sutskever, and Hinton. This is the big paper where they used convnets to beat all to like blow past state of the art on ImageNet classification. And
Mm.
when that came out, I was somehow that kind of shook my worldview and made me realize that there was some other possibility, and like that maybe we should think about how to use we should think about how to use deep learning for problems like
Mm.
robotics, and maybe that was the future. but it wasn't clear exactly how you would use machine learning for robotics or for tasks where there's some kind of action or interaction with the outside world.
Hmm.
Um, but then thinking about it a little more, it became kind of clear that the ultimate way to do this was reinforcement learning. Like RL
Hmm.
is RL is like the problem description that's relevant to training to getting agents that act in the world. So at that time, RL was kind of theoretic, like a lot more theoretical than it is now, and it wasn't clear which of the families of algorithms that are going to actually work. So I spent a lot of time trying to understand which RL algorithms um, were most promising.
Just some background for the listeners. So you started your PhD probably right when deep learning was kind of having this resurgence. In reinforcement learning itself, it was like just the first results were just starting to come out.
Yeah, yeah. So I'll say a little bit more about the chronology. So I started my PhD in 2010, and that was right around the time that there were some exciting results with deep belief nets
Mm,
from mostly from Hinton's lab, and I thought those results were pretty exciting, but it was also um, like not clearly revolutionary, and the ideas were kind of complicated, and it wasn't clear how general they were. So I think it was only starting to get it interesting at that time, and then it really picked up around. Then it really picked up in around 2012, a couple of years later, or 2013,
mhm,
and I started getting into reinforcement learning maybe early 2013, and that's before that was right before DQN, like DeepMind DQN results came out. There were some other there were some other good RL results that happened around that time that I can go into more. But yeah,
mhm.
that's a rough overview of the timeline.
Yeah, I see. So when do you remember like when you saw results like the DQN paper? Did you kind of know that it was inevitable that deep learning was going to be kind of incorporated into reinforcement learning, and that was the way forward? Or yeah, what was it like to be a researcher around that time?
Yeah, I'd say I was pretty sold on deep learning plus reinforcement learning a little before DQN. So in that way, I had a little bit of a head start over everyone else who just started to uh, look at it after that. Um, so yeah, at that point I was pretty sold on it. I mean, especially there are a lot of things we take for granted now that weren't that obvious back then. Like we were uh, like the whole idea that you can um, well, back then people were thinking about POM-DPs as something that was fundamentally much harder than MDPs.
Mm,
Like people were thinking about like in robotics, people were thinking about all sorts of fancy methods for solving POM-DPs,
mhm,
and it was generally considered to be a super hard problem. But then, and I had initially yeah, I initially thought it was hard, but then after thinking about it some more, I realized, well, if you just have an RNN, this will that effectively lets you look at the whole state, which is just the history of observations, and you can just
mhm.
training an RNN policy with policy gradients seems like it should be able to solve POM-DPs, and I was really blown away um, by this insight, and I remember giving a lab meeting talk about it, uh, and now it's kind of obvious, like everyone knows this, but it was exciting to kind of go through that thought process at the time.
And then you mentioned you were going back and trying to see which algorithms would be applicable. Did that have to do with this shift to deep learning, where maybe you were going back and looking at older methods and trying to see whether you could use or adapt something from the past that would work with the newer methods?
Yeah, that's exactly right. So there are a lot of different, totally different algorithms for solving MDPs, and it wasn't clear which ones were going to be compatible with using neural nets as function approximators. And people had worked on this a little bit, but the literature was still like pretty primitive.
Hmm. Yeah, I guess we could start going into the content of the thesis. So maybe just to start off, I mean, we've mentioned reinforcement learning many times now, but if you could just give like your own definition of reinforcement learning, and then at a high level, which aspects you chose to focus on during your PhD.
Yeah, I would say reinforcement learning is how to learn to act. So how to solve problems where an agent is interacting with an external world that's unknown to it. This contrasts with other kinds of learning where you have a loss function that is all like it's just a something you have analytic access to. Like in supervised learning, you just have a loss function, which is some nice differentiable function, and you optimize
Mhm.
it. But in RL, you're optimizing through some kind of unknown system is part of your optimization problem, and so RL is about how to deal with that.
You have a really nice, so in the background section, you have this really nice kind of taxonomy of different RL methods. So it's divided into like policy optimization and dynamic programming. And so from policy optimization comes these policy gradient methods. And then from dynamic programming comes these value-based methods like Q-learning. And you mentioned that at the time, at least, methods like Q-learning kind of weren't well understood and are maybe less stable than policy gradients. Where do you kind of stand on that today? Do you think by now people have sort of figured out how to get Q-learning to work good enough, or would you still prefer one over the other?
I think a lot has happened since I wrote the thesis, though the basic I think my like basic view there um, it still is holds true. So I think the policy gradient methods are simpler to understand and to analyze, and given a new problem, you're going to have an easier time getting policy gradient methods to work on it, especially if you're not if you don't care about sample efficiency that much. I think the value based methods will you can usually get them to work and get better sample efficiency once they do work, and they're still not as well understood. I still think we don't have. I still think there's a lot to do there in terms of improving them and making them more reliable. So they're just less well understood, but once you get them to work, they're more sample efficient, but usually less compute efficient. So I think
Mm.
one big question right now is we're not going to ever be in the regime where computation is free. So if you're in a regime where computation is expensive, I mean, when you're using really big models, then in what cases do value-based methods have an advantage?
Yeah, so still more to understand about
Yeah.
them. Yeah. And then, so your thesis, it's kind of structured into these three parts. So, trust region, policy optimization, the generalized advantage estimation, and then stochastic computation graphs. I thought we'd actually start with the last one. So, the stochastic computation graphs.
Mhm.
What is a stochastic computation graph, and sort of how does it relate to reinforcement learning?
Yeah, so stochastic computation graph is, you could call it a kind of notation or a general description language for a certain wide class of optimization problems that includes reinforcement learning. Yeah, it's a way of describing a problem where you have some random variables that depend on other random variables. Like you have, let's say, an action, which is a random variable that the policy samples, or a next state, which is like in an MDP where it's like the environment transitions randomly to a new state. So you've got
Mhm.
like random variables, and then you've also got some deterministic operations, like your neural net might have a bunch of different differentiable operations. So if you're given a description of your, like how you compute the loss in terms of these components, how do you compute the gradient of that loss, or really how do you get an unbiased estimator of the gradient? The ideas aren't like terribly new, or I feel like the like people have been writing down loss functions that involve all of these pieces for a long time, and and people know how to we're calculating the derivatives of these things, but every paper would have a different like description of how you calculate the gradient, and often like a very convoluted description. So I was annoyed enough at reading these papers that I felt like we should just write down a standard way of describing these problems, and like I felt like we should just like remove the need for everyone to do their own derivation or give a
Hmm.
standard method.
Yeah, it is a really nice, yeah, like a nice formalism that summarizes a lot of things. So like you talk about like the pathwise estimator versus the score function estimator. So the pathwise would be something like this reparameterization trick that people use in VAEs, right?
Mhm.
And then score function would be like policy gradient. Like looking back on this work, like do you still think that this influences the way you think about these problems, or
Yeah, definitely. I think uh, it's definitely my go-to method of figuring out how to calculate the gradient of something. Like if you have a policy gradient, if you want to calculate the policy gradient with when you have like entropy bonuses or you have some differentiable rewards,
mhm,
this is a good way to do it. Those are problems that come up pretty commonly. Like if the reward function is something you have uh, that's differentiable and you know it analytically, then you can use this kind of method to get a more efficient gradient estimator.
mhm.
I think it's just an easy. It makes the calculations easier if you just. This is like a mechanical way to do the calculation instead of having to think really hard about it each time.
So do you think that this has some implications for the way deep learning libraries are designed? Because I know a lot of the times people just implement their own policy gradient or something. Do you think that somehow we could program a stochastic computation graph, if that makes sense?
Yeah, I was hoping for something like that when we wrote the paper, and
Mm,
it there was some excitement about that. Like PyTorch had some features that were based, or they initially had a library that was based on this idea, where you could. I don't remember exactly how it worked, but they had some way you could add like reinforced type gradient estimators. It
mhm.
never quite. I would say this never quite came together because it turned out. Um, it turned out that like whenever you're doing something like RL, you you usually make a lot of approximations that or you take into account the structure of the problem to do variance reduction and other kinds of like improvements or speed ups. So for example, using discounting and you do discounting and value functions and so on. Yeah, somehow it hasn't been useful to put this into libraries because people want to do various domain specific tricks.
Sort of having the flexibility is, yeah, is important enough to not just incorporate it into the library.
Yeah. There were some ideas that we would uh, eventually have much more complicated models, or we would be doing hierarchical RL where there would be actions at multiple different levels, and
Mm.
this kind of thing would get really complicated, and it would be better if you had a library to figure out the gradients. But in practice, these methods never became that popular, and now very simple methods have are winning. And in those simple methods, there's no need for a library to calculate to do these calculations.
Yeah, so people thought the way to solve a PhD was with reinforcement learning with these hierarchical actions.
Yeah, that's right.
I think the main section I want to talk about is the one on TRPO.
Mhm.
Yeah, so maybe if you could just give an overview of what is TRPO first, and maybe how did you start working in this area? So this is like a model-free algorithm. How did you decide to focus your attention on that?
Yeah. So what is TRPO? It's so policy gradient methods are are kind of our reinforcement learning algorithm where, as it sounds like, you're trying to calculate the gradient of performance with respect to the policy parameters, and you calculate a stochastic gradient like we do usually in deep learning, and you take a small step in the gradient direction. But the
Mhm.
point of like policy gradient methods differ from other RL algorithms in that we're just directly trying to optimize the policy as opposed to doing something indirect like learning a value function and trying to use that. So
Mhm.
TRPO is like in so TRPO trust region policy optimization. The idea is uh, we don't want to take too big of a step in any kind of stochastic gradient descent. You don't want to take too big of a step because you just have a gradient, and if you step too far, your loss is probably going to get worse. But this problem is particularly bad in RL because the your policy also depends what your policy determines what data you're collecting. So if you take too big of a step, you're going to collect completely different data, and now you won't be able to fix your policy. So
Mhm.
unlike in supervised learning where the data doesn't depend on your current uh, your current function.
The consequences of making too big of an update kind of propagate in the sense that you'll start collecting bad data and then update on that bad data.
Yeah, exactly. So with TRPO, the idea is we introduce a trust region. So that means so a trust region in optimization is a smaller part of your parameter space where your local approximation to performance is accurate. So,
Mhm.
so one way of seeing why you have to take small steps in optimization is that uh, whenever you like what you do in optimization is you try to get a local approximation to your performance, uh, meaning you try to approximate what would happen if my policy or my parameters were a little bit different. And then you try to take a step in the improvement direction. But you're always using an approximation. So um, your approximation is only accurate around your starting point. And the idea of a trust region algorithm is you say, maximize my estimated performance subject to a constraint that I stay close to the starting point. So that's exactly what TRPO does. The algorithm is to get a local approximation of the policy performance, and then you take a then you maximize that local approximation subject to the constraint that your KL divergence from your initial policy is small.
Do you remember how you got this idea? Was it kind of from you could think about optimization just abstractly and maybe come up with this idea that you shouldn't update too far? Or is it from, I don't know, running a lot of experiments and you got some intuition that this type of update would be a good idea? Do you remember, like, yeah, what was the origin of this idea?
Let's see, there were a couple of inputs. So one thing you could contrast TRPO to is policy iteration, which is this algorithm where you don't do a small update. You first you collect a bunch of data, you fit your value function, and then you solve for the optimal policy, or you solve for the policy determined by that value function. So TRPO
Mhm.
is connected to that, but it does an incremental update instead of a big update.
Mhm.
So I would say the two papers that influenced me the most were this paper called "Conservative Policy Iteration" from Kakad and Langford from around like 2000. Um, and this was the idea there was they pointed out that policy iteration has problems when there's any kind of error in like in your estimating the value function. So they fixed it by not fully updating the policy each iteration. Instead,
Mhm.
they calculate a new policy and just take a mixture between the new one and the old ones, kind of like in boosting. That was one influence. Oh, and they had a lot of theory, and they had some very nice theory in that paper. And the theory in TRPO is largely based on their theory, but
Mm, I see.
I realized that they like there was a way to use their theory in a like in a more kind of practically relevant type of algorithm. And the other paper that was influential was there was this paper that came out. Well, I read it a couple months before 2013 NIPS called "Approximate Dynamic Programming Finally Performs Well in the Game of Tetris." It's a funny title, very very direct.
There should be an acronym for that.
Yeah, yeah, that's right. So it's just what it sounds like. They showed um, that you can do well in Tetris with. I mean, the problem was like Tetris has been an RL benchmark for a long time, but the RL methods have always been worse than like direct optimization in parameter space using methods like CMA.
Mm,
And this paper had a bunch of tricks um, that made approximate dynamic programming and specifically policy iteration work better.
mhm.
So So I had actually started out by I had implemented their algorithm, and I was getting pretty good results with it on the problems I was working on, um,
Mhm.
like much better than I was getting with other approaches. And I had also read the conservative policy iteration paper, and like I kind of I felt like the idea of the incremental updates, or taking these small updates, was very important.
Mhm.
So I ended up, like, I started out doing various hacky things where I would mix these two ideas together. But at a certain point, I realized I kind of realized that the way conservative policy iteration mixed together the policies, um, like that was basically just constraining that effectively constrained the KL divergence between the policies, and that was or the total variation divergence between the new policy and the data collection policy. And I realized that we can just come up with a like we can do this in other ways, and like the trust region method is kind of a more natural way to do this when you've got a more powerful function approximator like a neural net. So then I like implemented. I did various hacky versions of this, and then I kind of did it properly, and it worked really well. And that's kind of
Yeah.
that was the birth of TRPO.
Yeah, that's really interesting. Like a combination of, yeah, reading past ideas, thinking about what they're doing, but then also just trying to get something to work and then thinking about how to do it, maybe like in a principled type of way.
Mhm.
So then, speaking of principled, so like one thing in this paper is that there is this theory that's used. There's like this monotonic improvement that you show. Did that actually come after you got this to work, or before?
Yeah, I'd say that the theory, like figuring out all the details of the theory, came after getting it to work. Though I actually found that when I that doing the like doing the trust region constraint properly was pretty important to getting it to work reliably. So,
Mhm.
like the version that we propose in the paper uses uses the conjugate gradient algorithm. Like there's some details that like don't no one cares about anymore, but like the way we did it in the paper, we basically take the a step in the natural gradient direction, and then we shrink it to be exactly the right length.
Mhm.
So there's a certain KL divergence between the new policy and the old policy. I had first tried to do this in some hacky ways, but actually doing it correct, like doing a proper line search where you make sure that the like if you take too big of a step, you shrink it until it's the right size. Doing that
Mhm.
um, ended up being really important to getting the whole thing to work. So I think the theory, or that wasn't exactly what was in the theory, but yeah, I guess I'll say that doing it properly, like, did make a big difference.
Yeah, at the time, everyone was trying to use TRPO when this came out, and I remember your implementation with this like conjugate gradient and the line search. It was like this magic implementation that everyone was looking at.
Huh,
So I still have still have good memories of reading that code.
yeah.
It seems like maybe these ideas kind of stayed with you because you also worked on this algorithm called PPO,
Mhm.
and there seems to be some connections between the two.
Yeah. Yeah, PPO kind of came as a natural extension of PPO or TRPO. Um,
Hmm.
TRPO was like did well at a certain set of problems, but while I was trying to get it to work on harder problems, I ran into two issues. So I never quite got as good. I never quite was able to match most of the DQN results on Atari, and
Hmm.
and then the like the A3C results that came afterwards. TRPO, yeah, still I wasn't able to quite match those A3C results. So I felt like maybe the conjugate gradient is not that compatible with these deep neural networks. And I still don't
Hmm.
totally understand why. I mean, people have some theories about it. Um, Now people seem to think a better way to do this is KFAC. Like a better way to do a natural gradient step is KFAC, because somehow the noise in the when you're doing your like the second order information, you get um, with conjugate gradient is too noisy and it doesn't help very much. But
Mm-hmm.
anyway, uh, yeah, I felt like TRPO wasn't that good on these problems with larger neural nets and especially with RNNs. So I was trying to, around that time, like late 2015, early 2016, I was trying to get good results with RNNs. And I was interested in things like hierarchical RL and the early versions of meta learning, and I wanted RNNs to work really well, but TRPO was I was just having trouble getting good results with TRPO. And also another issue was that the it's hard to mix in other loss functions in with TRPO. So if you have like so TRPO, if you just have you're trying to optimize your policy loss subject to a constraint, then it's fine. But let's say you have other loss terms like a like some auxiliary prediction or like you have your value function loss. TRPO doesn't say anything about how much you should update on these other loss functions, and the
Mm.
conjugate gradient doesn't really do the right thing when you have like some parameters that aren't part of your policy computation but are doing something else like value function prediction. So anyway, I wanted to come up with a version of TRPO that just used SGD. Like the most straightforward thing to do is to use a soft is to use a penalty instead of a constraint, and penalties are basically equivalent to constraints anyway. So
Mm.
the naive version would be to just add a KL a penalty between the KL divergence of the new policy and the old one. And that actually kind of works. That's okay. But it's also a little bit hard to uh, get that to get a single hyperparameter that works through the whole training process and that works through multiple problems with that approach. So the PPO paper proposes a loss function, which achieves this same goal of um, it gives you the tries to update in the policy gradient direction, but tries to prevent the too big of an update. But it just
Mm.
is the version of the loss that empirically worked the best, and it seems to have been withstood the test of time, at least for the from through the past 3 or 4 years.
Yeah. Yeah, I see. Yeah, I think this one, like reading through this paper, it seems like it was a different motivation almost. Like this was really focusing on kind of the simplicity maybe, and less so maybe the theory. Would you agree with that? And in general, like, do you have some general view of like the place of theory in reinforcement learning?
Yeah, that's right. The PPO paper was mostly there wasn't a much of a theory behind it, and it's there's just kind of an intuitive justification, but it was more
Hmm.
the paper was focused on the just coming up with a simple method that seems to have some of the right properties, and there are some experiments showing that it was better than various other reasonable alternatives.
Hmm.
I have a kind of moderate view on the role of theory, so I think if you can like provide a theory um, that seems to be predictive of what happens in reality, then that's really good. I
Hmm.
think people overdo the theory a little bit, or at least the older RL literature overdoes it, and people put too much emphasis on the theory, and but the theories don't actually tell you which algorithms are going to work better. I think the theory is useful if it gives you a like a useful hint about what you should do algorithmically.
So you're at OpenAI now, research scientist and a co-founder, and one of the things that you guys worked on was this OpenAI 5 that used PPO. Could you, yeah, maybe just give a brief description of what OpenAI 5 was, and how did you, what was it like deciding to use this algorithm? Were you sure that it was going to be the answer?
Yeah. So OpenAI 5 is the it was a project where we applied where we did large scale RL on the game of Dota, a popular popular computer game, and
Mm-hmm.
we used self play, which is where you're not you don't have one agent playing against a fixed environment. You rather have two agents playing against each other, but you can still use a policy gradient method by just like you pretend one of the players is fixed, is the environment, and you calculate the policy gradient under that assumption. Um,
Mm-hmm.
and then you can do the same thing the other way around for the other player. And like unlike normal RL where you see your reward going up, here there's no reward that goes up because it's a zero sum game. But instead, you see that some kind of rating of the agent goes up as measured by its win rate against uh, other agents. So in
Mm-hmm.
particular, we looked at true skill, which is like a rating system where you have pairwise comparisons, like you do face offs and combine those to get a score. So yeah, anyway, so this was a project that was running for a while, and we started off just doing one versus one, like an easier version of the game, and then eventually scaled it up to five versus five, it's um, and it's the biggest uh, or second biggest one of the biggest RL experiments ever run. I guess the others
Mm-hmm.
are like Alpha Zero probably used a lot more neural net flops, but maybe less like computers, less like CPUs running video games. Less
Mm-hmm.
uh, StarCraft, the DeepMind StarCraft project was also a very large scale effort.
Mm-hmm.
So anyway, yeah, eventually we got a good enough bot that we were able to beat the world champions in a match, at least in a version of the game that was close to the full game, or it was basically the full game with some minor restrictions on like which characters were playing.
Right. Yeah. At a high level, I guess you could describe the strategy as take take a fairly like generic network architecture. So I think this was an LSTM,
Mhm.
and then use PPO and train this algorithm on just many games, and that was actually turned out to be sufficient to beat the human players.
Right. Yeah, and I was actually I wasn't the like making the decision on what algorithm to use. So I was only loose. I was only lightly involved, and I was actually kind of skeptical of the idea of just using PPO for the whole thing. Well, I thought it might work, but I figured, I mean, it's going to work with enough compute, but I don't know if we have enough compute to do this. But the people working on it just kept pushing it, and it turned out that it was enough.
Yeah, yeah, I see.
Yeah, I thought
In
maybe we should use other I thought maybe we should try value based methods or we should lean more heavily on behavior cloning, but it turned out
mhm.
that self play PPO went all the way.
In terms of like, I mean, it was obviously a massive accomplishment to to beat the human players. In terms of like a scientific takeaway, what would be some of your takeaways from this problem from this project?
Yeah, I'd say first it shows that policy gradient self play is actually quite powerful,
Mm,
and yeah, this very basic algorithm works quite well with some some tricks like one of the tricks was randomization where you randomize various aspects of the game. Like you make one player uh, have small advantage over the other. So policy gradient self play with randomization is quite powerful and actually surprisingly reliable. Whereas you might think
mhm.
it would diverge or get stuck in local optima or something, or run around in circles. Um, yeah, that's in fact, if you try to do self play training in general, on even on simple problems like rock paper scissors, you often find that you have trouble getting convergence. But yeah, with some of these with some generally applicable tricks, you can get it to work quite well.
Hmm. I
And
see.
previously, Alpha Zero had already shown that self play is extremely powerful, but they used a more complicated procedure that involves search. Um, so, uh, so they're it's not just like doing policy gradient. They're like calculating really high quality target distributions over moves. So
Mhm.
it wasn't clear that if you needed search or not to do well. And in fact, I remember various prominent people had predicted that it wasn't going to work well because it didn't use search, but that turned out to be wrong.
Yeah. Yeah, maybe when you're designing TRPO, would you have even thought that kind of one of the most important properties was the scalability at the time? And maybe nowadays we think of that as being very important.
Yeah, I did actually think about scalability as being important back
I
then.
see.
I thought like the key thing is to just like get an algorithm that works kind of reliably, and then we can like at the time we didn't seem to have algorithms that you could just we didn't have anything that was like plausibly really scalable that could solve really hard problems if you threw a lot of compute at them. Um,
Mhm.
so yeah, so I kind of so TRPO was designed to be somewhat scalable, but maybe I didn't appreciate
Mhm.
uh, all of the different properties it needed to have, and I didn't know that the like the certainly TRPO is a uses second order ideas, and I didn't know at the time that those weren't going to be as scalable. Um, I still don't. I don't think we still understand exactly where second order methods fit in, but
Mhm.
yeah, it turned out that that it so far they're well currently they're not the dominant approach.
Do you have a sense of whether we know what the limits are to this model-free paradigm, like whether they'll be sufficient for all of the use cases? Like here, I think maybe it was surprising to some people that we thought that maybe you needed something capable of doing like explicit planning or something like that in order to play Dota, whereas it was able to figure out something just on its own with this model-free method. Yeah, so like, what's your sense on model-free versus say like a model-based type methods?
Yeah, I'm still pretty much a still a strong believer in the model free methods. It's I think just on the principle that we should let our function approximators do all the work and all of the calculations that we don't know exactly how to do. So
Hmm.
with model based methods, we have to tell the network something about how to search or something about how to plan and or what to do with the model and how much to trust it. And I would rather just
Right.
have I would just train something, rather just train something end to end, so that the network itself can implement the best possible algorithm. So I don't think
Hmm.
it actually has any limits. I think it's actually kind of well. I don't think we necessarily there's some like open questions, but I don't think the I don't see any limits to model free RL. Except I think maybe even like a bigger source of problems is actually the whole alignment problem that if you have that it's hard to get RL um, systems to do what we actually want. That it's more likely that we'll like if we have a reward function, the algorithm will find some bad way to maximize it that we didn't intend. So
Yeah, I see.
I think that's a bigger problem actually.
Yeah. Do you think that that this alignment problem might be a place where our own intuitions or something have to be more baked into the solution? Or is there a purely data driven way of doing that?
Yeah, that's a really good question. I think some of the proposals for how to do alignment better involve kind of using a more handcrafted approach, like
Hmm.
sort of like handcrafting a little bit, like how the agent thinks. Um, Ideally, I'd like to like reduce the handcrafting as much as possible, but
Hmm.
we have to, yeah, somehow we have to insert, we have to like I don't know. We have to impose some priors somehow. Some of the more promising ideas are just like how to help people provide better supervision um, on the agents, or like using one agent to help supervise another one, like um, using like agents to help us critique other agents, that sort of thing.
Hmm.
I think like some of these ideas are promising, and some of them involve like doing more handcrafting of what the how the agent works. But I think those if you have too much handcrafting, this you're just not going to be competitive with approaches that are end to end.
Hmm. So yeah, those are the two sections that I want to cover from the PhD thesis. There's another one on this generalized advantage estimation.
Mm-hmm.
Before we move on to some things that you're working on now, one thing that I've noticed is that Berkeley has become a really great place for reinforcement learning research.
Mm-hmm.
And obviously, like you were part of the process of that evolution. Do you think that are there kind of takeaways that you have for what the environment was like there that made it such a great place to do research?
Yeah, I can't take too much credit for it. I think, though, yeah, I was one of the early people there doing it. I think it's probably just one of these things where there's a critical mass of people who are interested in, and that, and like more people kind of clustered together there. So people want to be around other people who are like at the forefront in their preferred field. So I think just the fact that like Peter Abil was like pushing this direction, and then Sergey Levin, uh, like just a whole that created a kind of a nice critical mass um, that grew, and also probably the proximity to like a lot of like some of the industry research labs in the Bay Area helped create a like helped let Berkeley become the kind of the epicenter. Well, I think Berkeley was a quite good environment for doing a PhD in that there was just like there's a good amount of like communication between the different AI groups. So we were all on the same floor and kind of knew each other. So I think it was easy to be exposed to a lot of ideas. I don't have didn't know any notice any other
Hmm.
specific features.
Yeah, yeah. No, I think that's probably what it is. Is that a lot of it comes back to the people.
Mhm.
So having a lot of good people interested in similar things.
Yeah.
So then after your PhD, I guess we talked about PPO, but yeah, so some other things like that you're maybe currently working on. Did you kind of continue streams of research from your PhD, or did you also branch out into new areas?
Sort of. Yeah. I think I've been sort of continually well, my focus has been continually changing
Hmm.
or gradually changing. Yeah, after I started at OpenAI, I was still mostly thinking about the how to about the algorithms and how to design how to make our algorithm like core algorithms better. So I looked into I worked on hierarchical RL a little bit. That didn't quite pan out. I looked at around the time of PPO. I was also thinking about the connection to value based methods. Then I started getting more interested in just how to get RL to work with how to get RL to generalize more. So it kind of bothered me that we're using RL is in RL we were mostly focused on optimization, not generalization. So it's like we have problems where there's a we have problems that are kind of in some simulation or in some game, and
Hmm.
we're trying to optimize score on that. But we don't think much about generalization to new situations,
Hmm.
and it doesn't really resemble the other parts of machine learning where we have these big diverse data sets. So I wanted to think about how we can get better generalization in RL, and if maybe that was the key to getting better sample efficiency. Maybe it's not we don't have that much improvement that we can squeeze out by just coming up with more clever algorithms. We should instead be trying to do pre-training or like somehow
Hmm.
train on a diverse data set as a way of speeding up learning something new.
Hmm.
Uh, so so first like meta learning or meta RL was kind of one project in this direction. So we wrote a paper about meta RL called RL squared.
Hmm.
Then I started getting like that was mostly in like that would only work in toy like small scale problems. So I got interested in how can we actually create big data sets. So we made this data set called Gym Retro, which is like lots of retro video games.
Hmm.
And we thought maybe if we just train a network on all of those, it'll generalize to new games.
Hmm.
That turned out not to work. It turns out that these games aren't they're kind of more conducive to memorization, not generalization. So you don't actually learn very much. You just kind of memorize one trajectory for each game.
Yeah.
Same with Atari. Then procedural generation. Then we basically realized we need to study the problem like more carefully and scientifically. So we don't really know how the performance scales with data set size. So let's just come up with a controlled environment where we can measure generalization. So that's when we started looking at procedurally generated games.
Hmm.
We figured let's just try to let's try to get generalization in this controlled setting and study how um, and once we have this, we can use it to like we can study things like regularization. We can study which algorithms are better. Um, so anyway, that ended up being quite fruitful for a couple of years. I think, yeah, the procedurally generated games are much better than Atari and some of the benchmarks people were using before. I don't recommend
Hmm.
anyone to use Atari anymore, or these Majoko like 2D tasks. I think these are kind of past their prime.
Yeah. 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 One thing that comes to mind as you're saying this is like, wasn't there a paper that you could train a reinforcement learning agent to play Atari, and then if you invert the colors or something like this, then it completely doesn't know what to do.
Yeah, yeah, that's right. I mean, uh, we're not really learning vision when we train these Atari agents. It's
Yeah. Yeah.
like so in the the ProcGen paper, we found that if you train on like 500 levels, you get a certain amount of generalization to the unseen levels. We have
Hmm.
like Mario like games where you have like a certain amount of randomly generated levels. So
Hmm.
so we can measure like as a function of the number of levels, how good is your test set performance? And we
Hmm.
found that if we create a game that looks like an Atari game, where we have like a deterministic sequence of levels, um, then you get basically no generalization at all uh, to any other levels. So you learn perfectly well on this deterministic sequence of levels, and you see a nice looking learning curve, but you don't learn
Hmm.
anything about the other levels. So we're just in a totally uninteresting regime when we look at tasks like Atari.
Yeah. So on this procedural generation, so I guess you kind of mentioned it there that the idea is that you could vary the environment and then train on many different instances and then generalize to other levels in that environment. Um, have you thought about like what it takes to generalize across different games? Is that still really challenging?
Yeah, yeah, I think that's the next challenge. Yeah, the problem is I think and that's what we were hoping to do with Gym Retro. But I think
Mm.
Gym Retro isn't a sufficient data set to do this, at least with current techniques.
Hmm.
So I don't, right. So we'd like to see generalization between games, but it's, I don't think we're ready to get that result yet.
Yeah, yeah, yeah. It's just this, like the results that have been coming out on like GPT-2 and GPT-3. It makes me think of this problem that potentially the answer is like set up the right large scale pre-training setup, and then some of these some of these problems fall away. Like you're able to just somehow do like generalization or few shot learning or things like that.
Yeah.
Yeah, I wonder if that'll end up being applicable in this context.
Yeah. I think you're right. I think that's the eventual solution. It's still not totally clear what kind of pre-training will help you on these sort of visual motor tasks. That remains to be seen,
Yeah, yeah.
but I think that's right.
Being at OpenAI now, I have to ask a question about general intelligence.
Mhm.
So I think so. Jan LeCun said that reinforcement learning was maybe going to be like a cherry on top of a cake, where the whole cake is general intelligence.
Yeah.
Do you have a sort of view of how reinforcement learning will play a role in?
Yeah. Yeah, some RL enthusiasts were offended uh, by Jan's statement there, and I actually think he's basically correct. Um,
Mm,
yeah, I think that's mostly right. That RL just it's hard to extract a lot of information about the world just using um, RL, unless you also include with RL like all sorts of auxiliary rewards or auxiliary predictions you might throw in. But
hmm
yeah, I think from say policy gradients, you're not going to extract that much world knowledge. So I agree with Jan that most of the learning comes from should come from some kind of unsupervised learning and also supervised learning when it's available. I think RL, but you still need RL. I think it's going to be like the problem with supervised learning is you have to cover every possible. Um, you're basically covering the distribution of all humans that you've asked to perform your task. So, like GPT has to learn a mixture of all humans, uh,
mm,
like whatever human might be typing right now. It's some mixture of all of those possibilities, and
hmm
that's not what you actually want. What you actually want is you want um, you want to do like you have a specific objective and humans might not be optimal at that and you don't necessarily care about covering all the possibilities. You just want like one policy that does a good job on your objective. So I think
hmm
just mixing in a little bit of RL, you can get a massive improvement by just narrowing down your distribution to whatever works.
Yeah, so you somehow learn this mixture, and then RL. Maybe the cherry analogy is not the best, but yeah, it somehow narrows it down to what you want to focus on for that specific problem.
Right. Yeah. I guess the cherry, the cake picture is sort of more about representation learning, like
Right.
where you learn about the world and learn good representations. So I
hmm
think, yeah, in the setting of doing like cloning and RL fine tuning, I would say it's yeah, it's a little different because it's more like uh, you're you're just kind of narrowing down your distribution. But I also I agree with the cake analogy that even if you don't have any cloning data, you can probably learn most of the representations from unsupervised learning and then just do a
hmm
little RL on top and get um, an agent that actually does something.
Yeah, yeah, that makes sense. So one thing you've wrote about in your blog is like how you pick problems. Um, so do you think that the way that you picked certain problems or areas to work on, did that change from when you were doing your PhD to now when you're at OpenAI?
Yeah, right. Yeah, I talked about idea like goal driven research, like solving a specific problem that's hard versus idea driven research. Yeah, I think actually the goal driven research is um, yeah, I still mostly agree with that advice, and I think it's probably good advice for most people, not for everyone, but yeah, it's usually good, especially until you have a really good appreciation of your field and like what are the open problems in it. I think after you have a really good understanding, then you can start to directly address the flaws in the current methods. But I think uh, it, like just trying thinking about how to solve new problems or problems that are hard is a pretty good way to go about coming up with figuring out what to do. So I basically still endorse that advice.
Yeah, this was good to go back, and it was really interesting to hear about like how the idea for TRPO was formed, and then how it got extended into PPO, and it's been applied to large scale problems now. So it's a pretty cool story.
It's been a pleasure. Thanks for having me.